Start of chapter 3, stoichiometry. A lot of this in this chapter is going to be reviewed from CP and honors. So let's get started. Stoichiometry is the relationship between chemical formulas and reactions, okay? But in a mathematical way, quantitative, okay? So with stoichiometry, we usually need balanced equations, and then we also need the math to go with it. So that way we can convert one chemical to another. So it involves a relationship between looking at reactants or products, or both, in a quantitative way, either using grams or moles or molecules, so forth, so forth. It's one of the most fundamental skills that you need to make sure that you have a solid foundation for an AP, because it's a topic that's not going to go away. So first scientist we're going to talk about, Antoine Lavoisier, French scientist. He's the one that's actually, it's his fault for balancing equations. He said no matter what, the law of conservation of matter, you could even say the word mass, okay? No matter what, mass is neither created or destroyed. But if it's not created or destroyed, then what happens? It's rearranged. But if it's rearranged or constant in that balanced equation, then what happens to that matter? Well, we create products and we lose some reactants, but in the end, it's constant. But you have to have this occur in a chemical reaction. Okay, so remember, there's always three parts to the law. And if it's a law, ladies and gentlemen, so it's not going away. In this chapter, take a minute before you move on. These are the learning objectives. So when you watch the AP dailies for 4.1 and 4.4, these are the learning objectives that AP expects you to learn and know and be successful at while you're doing this chapter of stoichiometry. So take a minute, read and annotate and make some notes before you go to the next section. First part, we're going to talk about physical and chemical changes. Now remember, this is changes. So first one is a physical change. All you did was undergo a change in properties. Okay, more specifically, qualitative properties, but you didn't change the composition. You didn't change who it was, what it's made out of. If you have water, as you see water as a solid and you made water as a liquid, the identity didn't change. So we call that the composition. Okay, so the identity didn't change. I didn't mean to put the word composition there. Didn't change. Okay, there's no bonds that are breaking in a physical change. You still have water, you have it end up with water. And we call this intermolecular forces. It's a very, very key important topic in AP. We're going to get more into it in chapter 11. But basically, you're just breaking the attraction between the molecules, not in the molecule, not the bonds. Breaking bonds, that's something else, okay? So examples, if you go from a liquid to a gas, a liquid to a solid, as you see right here, this looks like a solid type of structure for water. And as you probably heated it up, okay, you got some of the water molecules to, looks like these right here, look like about some gases. But notice the structure of it, the little tiny red one with the two white ones. I still got the red one with the two little white ones, okay? So all I did was just change the physical composition of it. I didn't change the identity. There's a couple ways that you can separate physical changes, as in filtration, distillation, chromatography. We did these in CP and honors. Okay, let's just do a little refresher. So these would be physical separations. I'm not changing who the chemical is. So filtration, so when we did the lab, we had like some sand, we had some salt, we put it in some water. The salt in the water dissolved. And we call that dissolution. Okay? So when something actually dissolves in water, the dissolution, you didn't create anything new. But the sand didn't dissolve. So what happens is when we filtered it inside of our funnel, the filter paper, it trapped the sand because the particles are too big to go through the paper. So then what happened is we have our salty water, which we call aqueous. Okay, so we took a heterogeneous mixture and we separated it physically, and then to get that salt water out, what we did was then we heated it up, took our Bunsen burner, we heated it up, we put it, I believe we put it in an evaporating dish, and what you notice is the salt was able to get separated from the water. Okay, so still it's a physical process. I didn't break salt and I didn't break sand. Okay, I just separated it from the mixture. Distillation is looking at the differences in boiling points. Okay, so if you have two substances with two different boiling points, the one that evaporates first. So evaporation is when you go from a liquid to a gas. So if I have two different liquids in here, let's just say alcohol and water. Okay, and let's say alcohol has a low boiling point, which means it can turn to a gas faster with a lower temperature, whereas water actually has a high boiling point and it boils at 100 degrees Celsius. And because it has a higher boiling point, it takes longer to boil. So that alcohol, the alcohol will actually turn into a gas first, and those gas molecules will travel down. This is called a condenser. And because it's surrounded by cold water, the water's not touching it. It's just surrounding a tube, so that way that gas will then turn back into a liquid. Okay, so now inside this round bottom flask, all I have is just pure alcohol. And this is how a lot of wineries, distilleries, breweries, this is pretty much how they make that over 21 type of substance, which we don't know anything about. Chromatography is when you're separating two or more different mixtures by having it interact with what's called a mobile phase, and it travels up the paper. So a lot of times we like to take inks, markers, and we did this before. Biology, they do it with leaves, you know, what is that stuff called? Chlorophyll. Chlorophyll, I forgot what that stuff was called. And we have water that's down here. And what happens is in the inks are blends of colors. Just like your pen that you're writing with, markers, they're a blend of colors. So what happens is some of the colors don't travel as high versus some of them travel higher than obviously the other ones. And that actually means something, and it has to do with polar versus nonpolar. Now, we're going to get more into that, as I said, in chapter 11, because that has to do with intermolecular forces. But basically, the sample is suspended in a liquid. Like I said, most of the time we like to use water. And you identify on how it flows through or around the liquid phase or that solid phase. So we're trying to see how high the pigments travel up the paper. And also, we want to see what colors were made out of that marker or ink. So like yellow is a primary color. All you're going to get is yellow. Or red's a primary color. But there's no such thing as green. Green actually can separate into yellow and blue. So you see a little bit of blue right there. I don't think you see the yellow part yet. Even a black marker. A black marker actually has all the colors blended together. So when we get to chapter 11, chromatography is going to come back, and we're going to look more into the details of why some pigments travel farther up the paper than the other. Dissolution, is aqueous. Okay? However, when I take that salt and I dissolve it in water, all I have is salt water. However, if I actually did break any bonds, attraction between the water and ions are formed, and usually heat is released. If I did break bonds, then that's a chemical change. But if temperature didn't change, then I just did a physical process. So one of the key things to know if a chemical reaction occurred is usually a temperature change. With a chemical change, you're producing something new, something completely new. You have a different composition. You have a different identity. So, bonds are broken, not physical change. Physical change, bonds are still intact. So with the chemical change, bonds are broken, and we have a new word for that. It's called intramolecular. Intra means the bonds in the molecule. How is this different from physical change? Well, if you look above, physical is intermolecular forces. It's the attraction between the molecules, not in the molecule. Okay? So that's the big difference. So if you're going to have a chemical reaction, you got to break some bonds and form some new bonds. So like one of the most famous equations, water breaks up into H2 and O2. I don't have water anymore. I have two elements that came from water. CO2 reacts with H2. Well, this is a substance called methanol. I don't have CO2 and H2 no more. I have a new molecule. Sodium reacts with water. Well, I create a strong base and I create some hydrogen gas. Completely different. So as you notice in the picture, these are called particle diagrams. And we got to be very good with particle diagrams. As you see right here, usually red is oxygen. So that looks like a diatomic oxygen. And usually white, that would be hydrogens. And because they're bonded together, that's also a diatomic. But when it came together, I now have new molecules. And that's water. Okay, H2O. So if you notice right here, the law of conservation, I have 4 red atoms, and I still have 4 red atoms over here. I have 2, 4, 6, 8 hydrogens, and I have 2, 4, 6, 8. The law is still intact, but I created a new molecule, which means that's a chemical change. Now AP is going to throw you lab questions, and the key is, how can you tell AP that a chemical reaction has occurred? Well, number one, did you form something new? Did you form a gas? Now be very careful with just saying bubbles, because remember, boiling, taking water as a liquid and going water as a gas, that's not a chemical change. Yeah, I got some bubbles, but I still got water, but in a gaseous form. Okay? So with that gas, sometimes you may see a change in mass, okay, because that's solid. Like for example, maybe I took like some sodium chloride as a solid, and I formed sodium, but I formed some diatomic gas. So what happens is this solid, maybe it's like 1 gram that you started with, and because you formed some gas, overall, they have to equal 1 gram. But doesn't mean the sodium that's left over is 1 gram. Part of it came from chlorine, part of it came from sodium. You formed a precipitate, and we know that word by now. We formed that precipitate, PPT, you can abbreviate that. Did you form some heat? Did the beaker get hot, or did it get cold? Okay, it doesn't always have to be heat. Did light get produced? Did an odor get produced out of nowhere? Okay, I always like to use the example of like brand new tennis shoes. Okay, brand new tennis shoes, they didn't smell when you left the store. But over time, as you wear them, those shoes, they do a reaction with your feet, get a little sweaty, a little stinky, and that's a chemical reaction that's happening between your foot, the sweat, and the sole that's in the shoe. Energy. Energy is big in chemistry. We love to look at how energy changes. Did I absorb energy, or did I release energy? And color change, okay, especially when we get to chapter 17, okay, titrations. Did I actually produce something new? So when we write a balance equation, we want to make sure that we indicate the state of matter. So for solid, gas, and liquid, okay, aqueous, aqueous means it dissolved in water. And if something dissolved in water, we put AQ. And here's the key word to where you also know if something's aqueous, is if they say the word solution. Well, what is a solution? Well, back in chapter 2, solutions, homogeneous mixture, when we looked at the matter chart. Acids are always aqueous, no matter if it's a strong acid, weak acid, and acids, majority of time, start with hydrogen, okay, majority of the time. We haven't got to acids and bases yet, but acids, regardless, are always aqueous. The arrow means to yield or to produce, okay? And chapter 15 is going to start the number one topic on the AP test, equilibrium. That means that you're forming reactants and products simultaneously. We call these reversible reactions. So in this chapter, we're not going to do with equilibrium just yet, but you do need to know the symbol of what equilibrium is. The triangle, usually you put this above the equation, and with the above the equation, that means that heat or electricity was applied. You could also have a catalyst that's added. And with that catalyst that's added, usually you would see, let's just say I have like A, B, and then I form A and B. And it doesn't have to be a decomp. It could be a combination. If I put a chemical on top of that arrow, one of the biggest catalysts that we use in AP is manganese dioxide. And manganese dioxide, it's not a reactant, it's not a product. It's a chemical that was added, and its main reason is to speed up the reaction, to make it go faster, okay? So with a catalyst, it's not a reactant, and it's not a product. It's just a chemical that was added. So we put it on the arrow because we don't want to balance it with coefficients. Now, in chapter 4, we're going to learn the rules of when something is a solid. And back in honors and CP, we looked at them. They were called solubility rules. So more specifically, I believe it's in 4.2, we're going to look at those rules. With a chemical equation, you have two parts. So you have to have reactants and you have to have products. And reactants are always written on the left side and products are always written on the right side. You can have 2 or more reactants, you could have 2 or more products, you can have as many as you want, but you got to have at least one on each side. We have to balance because the law of conservation tells us we have to balance. So we add coefficients, and coefficients are those big numbers in the front. But before we can balance, very important, okay, you need to make sure that your formulas are balanced. So if it's ionic compounds, you need to make sure that you balance your charges, your pluses and your minuses. So you need to make sure that you balance subscripts first and then go and balance the equation. So with subscripts, we're trying to balance the formulas. Be very careful when you're counting. When I have H2O, that means I have 2 hydrogens in that 1 molecule of water, and I have 1 oxygen in that 1 molecule of water. But if I put a 2 in front of that water, that means I have 2 water molecules. I have 4 hydrogens and 2 oxygens, but that 2 overall means I have 2 water molecules. So remember that matter can't be created or destroyed. So when we balance equations, we have to add coefficients and only coefficients. Very key. Don't ever change subscripts, because if you change the subscript, you change the chemical. Water is not the same thing as hydrogen peroxide. We are not drinking hydrogen peroxide. So if you have a subscript, do not change subscripts unless you balance the subscripts incorrectly. So once you have your what's called your skeleton equation, which means it's a equation with no coefficients. Okay, I like to call it like a naked equation. You need to make sure that the subscripts are balanced. So now that you have a skeleton equation, like for example, right here, if you count it up, my hydrogen and oxygens, they are not balanced. So we have something that we call atom inventory. We split the equation in half. So for carbon, I have 1, 4, and 2 oxygens, and on the product side, 1, 2, and 3. I have some hints to help you on who to balance first. So my hints are balance the metals first because they're the easiest. Then go after the nonmetals. But H and O, especially for combustions, they're always going to give you headaches. So always balance the H first and then the O second. So when I balance my equation, my carbons are already balanced. I'm going to go after my hydrogens next because I have a 4 and a 2. I'm going to put a 2 right there in front of the water. Remember that plus sign separates the CO2 from the water. So my hydrogen, that 2 goes for everybody in back. So I have 4 hydrogens, and my oxygens right here, I have 2 oxygens plus these 2, so I have 4. So my carbons are good, my hydrogens are good. Now let's fix the oxygens. I just need to put a 2 in front of this O2, and then now I have a balanced equation. You always want to make sure the last thing that you write is that balanced equation. So AP, and this is kind of a shocker when I see these tips that AP brings, you should double check your answer to make sure that each chemical formula has been written correctly and that your equation is balanced. You would be shocked how many times students on an AP test, not my kids are amazing, but students on AP tests, they forget to balance the equation, okay? And this key right here, which always shocks me too, do not ever put an equal sign. This is a balanced equation. This is not quantitative, okay? So please, no equal signs. Let's do a little practice. So write a balanced chemical equation using also states of matters. So solid calcium hydroxide reacts with a solution of hydrobromic acid. Okay, so right there I know my 2 reactants. So CaOH, and then solid, reacts with, so I'm going to do my plus sign, hydrobromic acid. Until we learn the rules of naming and writing acids, I will give you the formula. And remember, all acids are always aqueous. So no matter what, always aqueous. To produce, there's my arrow, water and calcium bromide. All right. Now, if they don't specify what type of water, then we're assuming liquid. And with calcium bromide, as you see the formula, and then aqueous. Okay. So this is called a skeleton equation. I have my my subscripts, I have my states of matters, and I have my reactants and products and my arrows. Okay, so now here comes the balancing. So we're going to list each element under the arrow. So I have calcium, I have O, I have H. Now because I have H in 2 spots, please don't list H twice. And then my bromine. So we're going to count up the reactants. So calcium, I see 1. Oxygen, I see 2. Hydrogen, I see 2. But remember this guy right there. So I have 3 hydrogens. And my bromine is 1. Don't erase. You're going to go through an eraser like crazy in this topic. So just cross it out. This is called your messy work. Hydrogen, I have 2. Oxygen, I have 1. Calcium, I have 1. And bromine, I have 2. So remember your tricks. Do the metals first. Calcium's my only metal. Well, he's done. Number 2, go to the nonmetals. But we want to leave H and O to the end. Well, I got bromine. I have a 2 on this side, 1 on this side. So I'm going to put a 2 here. Now by putting a 2 on bromine, I now have my 2 hydrogens plus these 2 over here. So now I got 4. That makes life a little bit better when it's not an odd and an even. So my calcium's looking good. My bromine's looking good. Now remember, let's go to H next. So I have 4 versus 2. So by putting a 2 in front of this water, I now have 4. But now look at my oxygens. They got fixed. And I didn't even have to put up a sweat. So what are we grading? We want the final answer right below it in a prettier box than you see right there. And states of matters, subscripts with coefficients. And that's how easy balancing is. And there you go. So you want to make sure, remember the tip that AP says, go back and double check your work. So for calcium, I got 1 calcium, I got my 2 oxygens, I got my 4 hydrogens, and I got my 2 bromines. All right, looks pretty good. Number 2, phosphoric acid. So phosphoric acid, I have H3PO4. Now remember, acids are aqueous. And potassium hydroxide are combined. So I'm going to put those together. Now, it didn't tell you what state of matter, so I would have to assist you. So I'm going to tell you aqueous. And we'll learn more about the rules for aqueous in Chapter 4. And it says the products are water. Once again, it didn't tell me what form of water, so I'm assuming liquid. And potassium phosphate, so K3PO4. Okay? Didn't tell me what state of matter, but I do know it's going to be aqueous. Okay? There's my skeleton, so let's balance it. So I have my H, my P, my O, my K, and I got O, and I got H again. So I'm not going to list them again. So on my reactant side, I have 3 plus the 1 here is 4. For oxygen, I have 1, but I also have these 4 over here. So I'm going to put a 5 instead. And phosphorus, I have 1. And potassium, I also have 1. For my product side, I have 2 hydrogens. I have 1 phosphorus. I have 3 potassiums. And my oxygens, I have 1 plus the 4. So then I have 5. It looks almost balanced, but let's go after those potassiums first. Potassium 3 versus 1, so I'm going to put a 3 here. And you never know, maybe this does help. So potassium now becomes 3. Well, I kind of messed up my O's and my H's, but let's fix it. I have my 4 O's over here. I have my 3 right there, so I'm going to have 7. And I still got 1 phosphorus. And my hydrogen, I have 3 plus these 3, so that is 6. Okay. Phosphorus is still looking good. So it looks like we just need to mess with the water. So for H2, I'm going to put a 3 right there. And 3 times 2 is 6. And my O's, I have 3 right there plus the 4. And that looks pretty balanced. So let's rewrite our balance equation down below, which I will let you redo that. Let's do a little bit of combustion, it looks like. I have a sample of C5H12O, and I do know that's a gas. Once again, I will tell you states of matters. Undergoes combustion by reacting with O2, and we know O2 is a gas, and produces CO2 and water. Well, CO2 is a gas, and water, in this case, a liquid. Well, we got 3 elements to balance, C's, H's, and O's. So I got my C5 and my hydrogen. Now be careful with these oxygens. Make sure right here, don't forget to look. I got 2 plus the 1, so I got 3. For carbon, I have 1, hydrogen 2, and same thing over here, oxygen, 2 plus the 1 is 3. If it helps you to write that little bracket at the top, so that way you look on both sides, please do. Because remember, it's what you put in the box, that's what we're grading. All right, let's go after those carbons first. So carbon, we're going to put a 5. And now my oxygens, 5 times 2 plus the 1 is 11. For my hydrogen is 12. And over here I have 2, which means I'm going to go 6. And then now my oxygens, I have 10 here plus the 6, so I have 16. And then my oxygens over here, I have 2 plus the 1. Now remember, I don't want to mess with this because if I put something in front of this molecule, everything I just did was pretty much for nothing. So I need to remember 1 plus something has got to get me to 16. So that means that something has to be 15. So I'm going to teach you a trick for diatomics. With diatomics, you can use fractions. And the reason why is because that fraction is always a number over 2. That's why it's called diatomic. So in order to do the fraction, it has to be an odd number over 2. And why an odd number over 2? Because, ladies and gentlemen, if you have an even over 2, that's called a whole number. We wouldn't be having this conversation if it was an even over 2. So because I need 15, I'm going to put 15 over 2. Now mathematically, what does that look like? Well, 15 over 2, and then because there's 2 oxygens, when you multiply by 2, cross multiply, and I get 15. That's how it balances out. So rewrite your equation, as you see right there, right here at the bottom. Number 4, we have MgNO3, and once again, I would tell you the states of matters until we learn the rules. So MgNO3, 2 as an aqueous, reacts with sodium phosphate, and aqueous. And it says the products are sodium nitrate, aqueous, and this magnesium phosphate, I do know, would produce a precipitate, aka a solid. Okay, so remember, if it's a precipitate, precipitate is not a state of matter, that's just what happened. So let's count it up. So I have Mg, I have nitrogen, I have O, I have some sodium, some phosphorus, and I have some more O's. So I see 1 magnesium, 2 nitrogen. For my oxygen, I do have it in 2 locations. So 3 times 2 plus the 4 is 10. For sodium is 3 and phosphorus is 1. On the product side, 1 sodium, 1 nitrogen. My oxygen over here, I do have 3 plus 4 times 2 is 8, so that looks like 11. And my phosphorus, because of that parentheses, that 2 goes not only for the O, but also for the P. So I have 2 phosphorus. Oh, my magnesium, I do have 3. Let's go over that magnesium first, because it's a metal. So by putting a 3, I now got to make sure that 3 gets distributed to everybody in back of that 3. So now my nitrogen, I have that 2 times 3, which is 6. For my oxygen, 3 times 2, 6 times 3, so I got 18, plus the 4 over here. Ooh, big numbers, 22. Let's go fix the sodiums. I have 3 here versus 1, so if I put a 3, that means everybody got 3. So you see why we always put our final answer in a box at the end? Because it gets really, really messy here. So 3 sodiums, now 3 nitrogens, and then the oxygens, 3 times 3 is 9. I want to make sure I didn't do something wrong. The oxygen, 4 times 2, so I got 17 going on right there. And my phosphorus, okay, that's why it's looking a little funky. All right, my phosphorus is 2 and 1, so I do need to know I put a 2 right here. And by putting a 2 there, I kind of messed up my sodium, but it's okay. We're going to fix it. So in that case, probably would have helped to gone to sodium or phosphorus first before sodium. So now sodium, 2 times 3 is 6. That's why I was doing a little pause right there. 2 phosphorus. And my oxygens, well, I still have 18 here. And then 2 times the 4 is 8. So I do have 26. Well, you can always erase coefficients. Let's erase that 3 because that didn't help us. But you can't change subscripts. So it looks like instead of a 3 over here, it looks like I need a 6. And I think that's going to help us. 6 sodiums, 6 nitrogens, and then 6 times 3 is 18. And then right here's that 8, and look right there. There's our 26. So I have a coefficient of 3, 2, 6, and a 1. So let's put that in our box, and we did pretty good. The next learning target that AP expects us to have some great skills on are particle diagrams. So take a minute to read the objective. You'll see more of these in the video AP Daily 4.3. Particle diagrams, now your AP test is not in color, it's in black and white. Okay, but so you'll see a couple of those in just a second. Number 1, it says that the red ones are oxygens. So let's do a little color coding here. So the red are oxygens. And it says that the blue are nitrogens. So let's get a little red and blue action. So I'm going to keep track. All right. Write a chemical equation for the reactants and the products. All right. So let's see what I got. I got some N attached to an O. So remember that O is oxygen. And I have 1, 2, 3, 4, 5, 6, and 7 of these. Okay, so I know I have NO. Now I'm not going to balance it yet, even though I know I got 7. And I know NO is a gas because nonmetals with nonmetals are usually gases. Usually, notice I said the word usually. And then I have diatomic oxygen. So with this diatomic oxygen, this O2, because they're together bonded, then I'm going to put O2. And now on the product side, I have a nitrogen with 2 oxygens, and that's the only thing that I see over here is that NO2. The atom that's in the middle, the central atom, he's always written first. Okay? So I wrote a skeleton, but I don't have a balanced equation yet. Okay? So part B, let's balance it. Not looking at the picture yet. So for N, I have 1. For oxygen, I have 1 plus 2 is 3. And on this side, I have 1 and 2. Okay? Well, I can use a fraction, but I want to show you both ways without the fraction. So with a fraction, to make life simple, I can just put, remember I have 1 here plus something has got to equal 2. Well, that something must be 1. So I could put a 1/2. But part C says, is the diagram consistent with the law of conservation? Well, when you're doing this, you don't want to look at balanced equations that have fractions, because you either have it or you don't. Okay, so remember, to get it out of a fraction, basically if you multiply the whole thing by 2, you get rid of that fraction. So 2NO for every 1 oxygen and 2NO. Okay, so remember, because that 2 goes here, and then 2 times 1/2 cross multiply becomes 1, and then 2 times this is 2. Okay, so notice right here, for every 2 molecules, I have to have 1 oxygen. So if you count right here, what did we say we had? 1, 2, 3, 4, 5, 6, 7, 8. Did I count that right? 1, 2, 3, 4, 5, 6, 7, 8. So according to my picture, let me do this, I have 8 of these. And for the diatomic oxygens, what color are those? I probably should have circled those in red. 1, 2, 3, 4. I have 4 of those. Well, yeah. According to my picture, for every 8, I have 4. 2-to-1 ratio. So that means because both of these have a coefficient of 2, they should match up together. And if you count, 1, 2, 3, 4, 5, 6, 7, 8. And there it is. Is the law consistent? Yes, it is. The law is valid. How would you know if the law isn't valid? Well, then obviously they wouldn't match up in mass. Let's try another one before you guys try one yourself. To be consistent, how many NH3, looks like that subscript got a little cut off, NH3 molecules should there be? Okay, so to help you with this, the blue ones are nitrogens. So that looks like diatomic nitrogen. Okay, so I know that's one of my reactants. The white ones, and I'll do white and black. The white ones are always hydrogens, and there looks like another diatomic. So it's telling me that in my picture, I'm going to form ammonia, which is NH3. Question is, how many should I be producing? All right, well, I first got to balance my equation. All right, so nitrogen the gas, hydrogen's a gas, which means I'm going to form a gas. I mean, it's a no-brainer, ladies and gentlemen. I'm not forming a solid, liquid, or aqueous. So if I balance my equation, I have N and I have H. So I got to count it up, 2 and 2. Nitrogen 1, hydrogen 3. Let's balance those hydrogen, and I'm not going to do any fractions. 2 on this side, so put a 2 there. And then 2 times 3 is 6. And then over here for my hydrogen, I'm going to put a 3. And then that'll be my 6. Okay? Because I didn't have any crazy work, I'm just going to go ahead and box that. But let's notice the ratio. For every 1 nitrogen, I have to have 3 hydrogens. Okay? So if you group it together, for every 1 nitrogen, I have to have 3 hydrogens to react with it. And right here, for every 1 nitrogen, I have to have 3 hydrogens. And I do. And for every 1 nitrogen, I have 3. We call this goes to completion. And this is going to mean something to you when we get to the end of the chapter, 3.7. What happens if there's one atom or molecule that's not being used? Okay? So if every molecule is being used, goes to completion, that means the reaction is finished. It will only produce what it produces. Okay? So now the question is, well, how much should I be drawing of my ammonia if this is what I'm starting with? So I have 3 nitrogens. And if you count up your hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9. So how many ammonias should I be producing? Now take a minute, think about it. If it's a 3-to-1 ratio, how many ammonias? Hopefully you guess 6. Okay? And here's why. Let's say for my nitrogen, let's do a column right here in the middle. Okay? Because right here it's a 1 to 3 to 2 ratio. Okay? If I double, well then he gets doubled. And 2 gets doubled. Okay? Well, if I do that again, 1 times 3 is 3. 3 times 3 is 9. And 2 times 3 is 6. So in my final picture, I should be drawing 6 ammonias. Okay? So when you draw ammonia, nitrogen, because it's the first atom listed, is in the middle. Okay? So I know I'm going to have to draw 6 of these. So I'm just going to go ahead and draw my blue atoms. And you want to make sure when you're doing drawings that the nitrogen are all the same size. Now, because I can't draw white, I'm just going to draw the black. And I got to put 3 hydrogens attached to. So kind of do like a north, south, east, west. And we're going to get into the drawing rules more in chapter 8. and 9. But hydrogen is smallest. So you want to make sure those hydrogens are way smaller than nitrogen. Okay, remember on the periodic table, nitrogen has 7 protons. Hydrogen only has 1. They're very, very small. Okay, so once again, I would draw 6 of those gas molecules. And because they're gases, you got to give them some space in those particle diagrams. If they were solid, you'd be drawing all your solids down here at the bottom. Or if they were liquids, okay, liquids would be like if it flows. Okay. In the rest of the video, I want you to try yourself. You have this example and this example. So this is how AP does it, where they different color code the black and the white. And if there's a third one, they draw it with like a little pattern or a plaid type of pattern onto it. And so first, make sure you balance the equation and then pay close attention to how many you have. So that way you know how many to draw. Okay. Before we do the next video, I'll see you on the next one.